we can just informally introduce ourselves, I think.
Okay.
Yeah. My name is Fetwi. Myself and Dr. Jessica will be chairing this session. Yeah, I'm from SQU. So nice to meet you all. And I think Jessica proceed then.
Thank you, Professor Fetwi. It's an honor to share this session with you. Welcome all to the 13th session. And I would like to start when the people add to this session, no? I think that I have to wait 2 or 3 minutes, more or less, because the 3 minutes left to start this session. I think that people is in the speaker, no, in the first session.
Yeah. I have a question.
Okay.
Yes, Ahmed. Yeah.
Do we need to introduce ourselves at the beginning or just start the presentation directly?
You will introduce yourself.
Okay. Okay, perfect.
Yeah.
Thank you.
Okay.
It's only 15 minutes for the presentation.
True.
And the last part of the presentation, we have 15 minutes with questions and answers.
True.
And we can discuss the different presentations.
Yeah. So maybe before I give the session to Dr. Jessica to start, just some reminders. As Jessica already mentioned to us, we have 15 minutes for the presentations. And so we need to stick with that. So Jessica maybe will remind you when we reach 13 minutes, she will give you the reminder so that you will wrap up your presentation. Then I would also like to ask you all, when you are presenting, please, if you can't turn on your video so that because the session is being recorded. So it will be nice if you can turn on your video. The other thing is, as Jessica already mentioned us, the question and answer will be, it has its own session after we complete all the presentations. So we will have 15 minutes for that. So all questions and questions will be forwarded to us through the chat session or to the chat. So I will collect them and I will be presenting them to respective presenters. And the last one, I would like to remind you all, this session is being recorded, so please understand that as well. So without further ado, I just give it the session to Jessica to lead the presenters. Yeah, thank you.
Thank you, Professor Fetwi. I think that we are 16 participants. We can start the session. Let me to introduce you to Hamed Mesli and Robert Fryer from the Thomas Jefferson University, Philadelphia, are presenters with work entitled Towards an Affordable Zero Energy Refrigerant Cooling Device for Hot, Dry Climates. Please, you can share your presentation, Hamed.
Okay. Hi, everyone. I hope you can hear me. So I will be sharing my presentation just in 1 second. Okay, so you can see it now, correct? Dr. Jessica, can you see my presentation?
Still coming, yeah.
Can you see it now?
Seems it is taking some time.
Yes, we can see.
It says,
okay.
Now we can see.
Okay, I think I can turn my camera off because it might be taking some of the internet just to be smooth during the presentation. So briefly, let me introduce myself. My name is Ahmed Nusalhi, and I am a lecturer at Maine University and a researcher at Thomas Jefferson University in the US. And I work as an architect and energy analyst. And also I work with the United Nations Association as a Sustainable Advocate and Sustainable Designer. And I obtained the 2021 Sustainable Design Award. And now let me go ahead. So Professor Gupta just made it easier for me from his presentation in the previous session when he was talking about that we need an innovative design solutions for tackling the overheating problem, which is the one I'm going to be talking about today. So I'm presenting today on behalf of myself and behalf on Professor Rob Fryer to talk about towards an affordable zero refrigerant cooling device for hot, dry climates. In the last 10 years, as you see, climate change has increased the average rate of temperature rise more than any other time in the last century, especially in hot, dry climates such as Egypt. But we didn't choose to work on this climate just because it's super hot. We chose it because it's located in several areas of the globe, such as the Arabian Peninsula, Asia, the Middle East, South Africa, Australia, the United States, and even South America. And now get ready for some shocking facts that I'll throw on you. On August 2020, California recorded a temperature of 54 degrees Celsius, which is 130 degrees Fahrenheit. And according to the WMO, it's the third highest temperature ever recorded on planet Earth. Moreover, on July 2020, the country of Kuwait recorded a temperature of 53 degrees Celsius, which is 127 degrees Fahrenheit. I just need you to imagine how much people are suffering and will suffer in the near future from the overheating problem. The majority of people will, turn on their ACs, but not everyone can afford an AC because it's very costly. Achieving thermal comfort in hot, dry climate is unaffordable for low-income residents, especially in the Middle East. Just imagine if you have nowhere else to go rather than the fridge to achieve your thermal comfort. And in terms of health threats, the effects of hot, dry air and high temperature are increasing the chances of skin diseases. But there's a common misperception here that I want to hit on, that most people think that high bacteria dies in high temperature, which is partially true. The temperature needs to be super high in order to kill bacteria. And if we look closely at this chart, it demonstrates that bacteria dies at a very high temperature of 65 degrees Celsius. But the temperature of 30 to 45 is optimum for the bacterial growth, resulting in heat allergy, rashes, abscesses, and several skin diseases. One examination that was published demonstrated that for each 1 degree Celsius increase in a normal temperature, the rate of hand, foot, and mouth illness, expand by 10%. Can you imagine 10% just for each 1 degree Celsius increase? And the common way to deal with such temperature is by turning on our AC. And because those ACs, are not affordable by everyone, and people in the Middle East spend more than 50% of their income just to cool themselves. So let's, briefly understand why are they paying this high amount. So if we are using 10 100-watt light bulbs for 1 hour, so we are using basically 1 kilowatt hour per only 1 hour. And for Egypt, this 1 kilowatt hour will cost you 1.45 Egyptian pounds. So let's take a more detailed calculation. If a family of 4 are using 2 air conditioners, they will be using approximately 648 kilowatt hour a month, which will cost them 940 Egyptian pounds. And a typical low-income family in Egypt will have an income of 1,200 Egyptian pounds a month. And now, get ready for the shock. If they are paying 940 Egyptian pounds for electricity, that means that they are spending 78% of their income just on electricity. And I don't want to comment on that. But take care, it's not only about the money. The expanding use of heating, ventilation, and air conditioning systems are responsible for 28% of the annual carbon dioxide and global greenhouse gas emissions, which are responsible for the temperature increase, basically. That means that if people were able to afford conventional air conditioners for some reason, the trade-off will be releasing a tremendous amount of greenhouse gas emissions and carbon dioxide. And as you see in this book, Brad Fleming and Roberts, I guess all of us read it, he mentioned that in the Sustainable Design for the Built Environment, that CO2 levels are at the highest point since 800,000 years ago, which are 410 parts per million. He wrote that we are in the middle of one of the most impactful periods of geological change and one of the 6 largest extinction events in all planetary history, which means an unsafe future for our future generations. They didn't do anything, but we are just messing the world for them. But there's a question that everyone I'm sure is asking, why don't we go passive? Why are we looking for mechanical systems? Unfortunately, the existing buildings decisions have already been made regarding building massing, orientation, window to wall ratio, envelopes, and material selection, which makes the introduction of passive design solution unfeasible. As a result, passive systems can be a good response for new buildings that are not built yet, but for existing buildings, it doesn't make sense and it's totally unfeasible. Like, for example, I cannot remove like my wall and make a wind catcher instead of it. In Egypt, buildings envelope are designed without even a single layer of insulation, and residents cannot afford major energy upgrades to their building envelopes to achieve thermal comfort. They need a practical solution, a more affordable and efficient mechanical cooling system that does not contribute to climate change. And remember the problem when we were talking about achieving thermal comfort at the beginning of the presentation, that it's unaffordable. You will never see such a picture like that in Egypt. All mechanical systems needs to be on at least for 12 hours a day. AC is more than life back there. We need to find a way that offsets the global cooling energy demand without harming the environment. The Middle Eastern countries must be on the front line of this campaign because, as you see in this chart, it was ranked as the top energy consumer in the Middle East for the 2016. The energy demand for cooling in the Middle East has risen significantly in the past 30 years, and it's predicted approximately to triple by 2030 compared to the 2010. But, what if we just ignore that and kept using conventional air conditioners and emit greenhouse gases and warming the environment? We will not wake up one day and see the Earth doesn't exist anymore. The Earth is not going anywhere. We are. If we continue to warm up the planet, it's not going to be suitable anymore for the human beings to live on it. Hydrofluorocarbons, also known as HFCs, are one of the main refrigerant gases that exist in a lot of our existing air conditioners. This figure shows that the global HFC consumption doubled from 400 million tons of carbon dioxide to 1,100 million tons between 2000 and 2010. Notably, more than 80% of that consumption was used for air conditioning. And just keep in mind that we only took one type of refrigerant as an example. But as you can see in this table, the most common refrigerant contribute to either ozone depletion potential or global warming potential. And now it's time for the interesting question. Do buildings get cancer? All of us know that cancer is caused when cells double abnormally and spread rapidly in the body, resulting in a weak body with no energy. And that's because, these cancer cells steal the energy and nutrients from neighboring cells and then eventually causing the cells to die. This is exactly what conventional air conditioners are doing within buildings. Some buildings appear to have a cancerous growth as air conditioning units that use refrigerants multiply and spread rapidly across the entire structure, leading to wasting buildings' energy, people's money, and damaging the atmosphere. We need to develop a solution that achieves thermal comfort without acting as a cancer tumor. I'm not hoping to see such a picture like that in the future. And despite the technology era that we are living in, ACs, the commercially dominant cooling technique, remain dependent on refrigerant, consume a large amount of energy, and increase the global warming. These are the three aspects that our solution will focus on: refrigerants, energy, and global warming, as I just mentioned. Therefore, our solution is going to be through using something called the thermoelectric Peltier modules with an innovative cooling system that has not been used before. But before I just talk about the method, let's jump 200 years back. In 1820, Thomas Seebach discovered a way to produce electricity through temperature. He created through a temperature difference by creating the different contact between two different metals. The temperature difference created an electronic movement from one side to the other, resulting in an electric current, which everyone knows about that. Later on the 1830s, Jim Peltier discovered that the Seebach system could work in reverse, creating a temperature difference, which we will focus on. Simply how it works: when a current is applied to a Peltier modules, it transfers the heat quickly from one side to the other, creating a huge temperature difference between two semiconductors. Thus, one side becomes extremely hot and the other one becomes extremely cold. The thermoelectric cooling is a high-efficient, silent operating system with no moving parts, refrigerant, and the most important part, it doesn't have any greenhouse gas emissions. But the big problem that these models are not capable of cooling bigger spaces. It can only cool small spaces, such as computer enclosures, small fridges, cars, electronic boards, and others. Thermoelectric modules were found approximately 150 years ago. However, they have only become widely used in recent years. Despite the effort made and experiments done by researchers in the era of thermoelectric cooling, none have reached a solution that performed as a conventional air conditioner with a high cooling capacity. After several experiments I have done, finally one of them worked, and I was able to reach a device that almost performed as a conventional air conditioner. Its innovation lay in using hybrid cooling system by combining thermoelectric and evaporative cooling. The schematic design consists of 3 cooling phases: thermoelectric cooling, air velocity enhancement, and humidifying. The first phase consists of 4 thermoelectric TEC-12706 filtering modules. These modules are responsible for cooling the hot air first before sending it to the next 2 phases. And as you see, the second phase and the next phase, which has the innovation in it, consists of something called a cooling chamber and the 308 CFM high-speed fan. When the device begins to operate, the filtering modules cools the air, and then the cooling chamber and fan decreases the air temperature further through increasing velocity. The last phase that we have, which also interesting for me, it consists of a biomimetic evaporative pad and a water tank and a small water pump. After the air is cooled and its velocity is increased in the first 2 phases, the evaporative pad humidifies the air and cools it further to increase the cooling efficiency. Another challenge that I had to face is the design of the evaporative pad itself. I was, just asking myself, what should the pad look like? And what is the humidity rate that it should produce? And after that, I realized instead of asking myself, I can ask nature. One way to design an efficient pad is by mimicking nature, since nature has proved its efficiency in species design and performance. I realized that we have an efficient organ that stays moist that I'm using right now, which is the tongue. It was discovered several years ago that tongues play a significant role in the evaporative cooling process in humans and other species. For instance, when dogs exert physical effort, such as running, their body temperature rises, and then they start panning as a cooling method. The tongue batten distributes saliva through it, allowing the hot air to cool down through evaporative cooling, which is like a natural system that we have by God in our tongue. Therefore, the pad design was inspired by the tongue surface. As you see in this picture, I hope you're seeing it on the same time that I'm talking about it. You're going to see on the right, the tongue under the microscope, and the inspired pad is on the left. The pad is formed with a curvy, smooth shape similar to the tongue to enhance the water distribution, while the voids allow the air movement in it. It was made of terracotta clay to stay moist. The prominences in the front of the voids are...
2 minutes left.
Yeah, I only have 50 seconds. Don't worry, doctor. The prominences that I was talking about in the front of the pad are meant for temporary water storage to improve the cooling process by adding more water to the air, flowing through the voids. And after putting all these together and turned on the device, unfortunately, it did not work. The temperature was increasing instead of decreasing. And I was looking for the problem in it. It was determined that the cooling chamber was semi-opened and needed to be further closed in order to give the filtering modules time to cool in air 1. Therefore, I redesigned the cooling chamber with a new small vent. Also, a moist cloth was added between the cooling chamber's vent and the evaporative pad to avoid any potential heat gain between the 3 phases. And I turned on the device again to see the difference. And finally, as you see in this chart, I was very happy when I saw the results. The temperature decreased from 78 degrees Fahrenheit to 66 degrees Fahrenheit. The device was able to produce air that is 12 degrees lower than the room temperature, and also the humidity increased by 30%. As a result, the invented device, which has a patent pending, consumes 72% less energy than conventional air conditioners while preventing greenhouse gas emissions. The operation of a conventional window air conditioner consumes 324 kilowatt hours a month, while the new hybrid system that we invented consumes only 324 kilowatt hour a month. Finally, if a low-income family in Egypt used 2 hybrid air conditioners rather than 2 conventional air conditioners, it would cost them only 22% of their income instead of 78%, thus reducing the operational cost by almost 3/4. These are my references, and I'm sorry for taking too much time, and thank you, and I was happy to be with you today.
Thank you for your interesting presentation. You are on time. And I would like to introduce the next speaker. I think that is sorry for my pronunciation, Shotaku Okamoto from the Tokyo City University. with a work entitled Study on Illuminance, Brightness, and Productivity in Japanese Office Buildings. You can share your presentation, please.
Okay.
Thank you.
Sorry. Good morning. I'm Shota Kokan from Graduate School of Environment and Information Studies, Tokyo State University in Japan. I can't English well, but do my best. Today I'm talk about my paper, study luminance and brightness and productivity in Japanese office buildings. And there are three parts this presentation. Firstly, overview of my study, and secondly, explain the methodology, and finally, I show the result of my research. Firstly, I talk about the background of my research, and this figure is show the energy consumption of office in Japanese during the summer and the winter. This figure shows that lighting about 30% of energy use of office, and so reducing of lighting use is important for energy savings. And so what the energy consumption of lighting, and this figure show the comparison of lighting standard in offices in various countries and the evolution of lighting standard in Japan. The horizon line is show the illuminance, and vertical lines are illuminance, and the horizon line shows the year and standard was established. And the illuminance standard in Japan is set by JIS and Japan Industrial Standard. It has been rising in 1985 and currently at 715 lux, and this is probably due to the change the workstation, but this JIS standard is higher than other countries. For example, the WELL standard in US is 300 lux. And therefore, the objective of my research is to understand the present condition of luminance and the brightness and productivity in office building in Japan, and to compare the luminance with the JS and other standards. And secondly, I explain the methodology of this research. We have the 11 office buildings in Tokyo and Kanagawa, and the period is from August of 2014 to September of 2015, and the number of measurements of 4,600. The survey was conducted once a month with actual measurement and questionnaires. The following data was measurement in actual survey, and this research used illuminance data, and questionnaire the following the item were asked to office workers, and this research used brightness sensation and brightness preference and productivity, and this table is actual questionnaires. And thirdly, I talk about the results of my research, and this figure shows the distribution of illuminance. This figure shows mostly distribution within JIS standard and some distributed WELL standard. And this figure, right side, shows the average luminance for each office. So mostly office within the GIS standard, but Office P1 is below the GIS standard. So Office P1 within the well standard, and focus on the three office B1 and B7 and B11. The B1 is much lower than the standard value, and B7 is higher than standard value, and B11 is line with standard value. So in other words, we can see the offices with various luminance distributions. And in order to investigate why the luminance of B1 is low, and I analyzing this. And this table shows the occupation of the office workers in each offices, and they are used desk light. And this table shows 30% of B1 office worker use desk light more than other office. And I think the occupation is design workers. I think the design job mainly use the PC, so they can work the low luminance office, and the worker who prefer brighter light use desk light. And right side figure shows desk light users rate by age group, and older worker use desk light than younger workers, and therefore the relationship between luminance and brightness is affected by age, and this is the same result of previous research. And next step is analysis the result of survey questionnaires, and this figure distribution of brightness sensation and brightness preference, and brightness sensation asked to office worker about how do you feel the current luminance level, and brightness preference and ask what do you want to do the luminance. And this figure shows the most common answer of brightness sensation is number 4, the neither bright nor dim. The common answer of brightness preference is number 3, no change. So the most worker are satisfied with the luminance. And next, to analyze in more detail, we focused on B1, B7, and B11 to distribute the questionnaires. First, the brightness sensation is almost same result. Number 4 is most frequently. But only B1 is a little more than number 3 answers, so slightly dim. It is B1 is a low luminance office, and the distribution of brightness preference is similar to the brightness sensation. So percentage of number 3 is highest, but unlike the result for brightness of B1, the answer percentage number 2 is which bright is same as offices. It is different from brightness sensation. In other words, the B1 office worker feel dim, but they want to do no change it. and productivity is the same of each office, and therefore the sense of brightness and productivity are considered to the same office with a different illumination level. And this figure shows a correlation between illuminance and brightness sensation. The vertical line is brightness sensation, and the horizontal line is illuminance, and the color dot is a building number. This figure shows that there is no correlation between the brightness and illuminance. So this result is similar to previous research, Nicole. And this is a conclusion of my research. Indoor illuminance of most of office is building is similar to GIS standard, and however, the illuminance of one office is similar to WELL standard, and there is no significant differences in productivity by building, and there is no correlation between brightness sensation and illuminance, and thus office workers exposing similar lighting environments. Thank you for watching.
Thank you very much for you adjusting the presentation to the request time. We can work in this presentation with some questions in the last 15 minutes. The next presenter is Daniel Cepeda Rivas from the University of A Coruña, with a presentation entitled Passive and Low Energy Architecture for Social Housing in a Hot, Dry Climate, Building Performance Correlations with Geoclimatic Features. And is co-author my friend, Jose Roberto Garcia from the Metropolitan Autonomous University of Mexico. Thank you.
Hello. Should I share my video? Can you hear me to begin with? Okay. Oh,
we can see your screen.
Okay, 1 minute. It's just that I got the wrong screen. Okay. Okay, can you see everything now? Okay, so yeah, my name is Daniel. I'm a PhD student at the University of A Coruña in Spain, and I'm presenting this work that is part of my PhD. I graduated in collaboration with my thesis director, Jorge Rodriguez Alvarez, and my friend, but another colleague from Mexico, because I'm Mexican, Jose Roberto Garcia Chavez. As we all know, pretty much we have been hearing this the whole time. Global warming is affecting everything around the world, and Mexico is not the exception. Temperatures have been rising together with the averages and the peaks. The thing about global warming and the effect it has been having around the world is that meanwhile the highest temperatures increase, it's occurring at the poles. The tropical and subtropical zones are the zones recording the highest temperatures, like the peaks and absolutes. And the problem with this is that most of these zones are developing countries that are not well prepared enough to survive this. I mean, things are very difficult in most of these countries, and unlike others, people just might die because of this, because of the economical vulnerability of the population. So in order to somehow collaborate in this research gap that exists, we decide to focus in Mexico as a whole country. Well, at the beginning it was as a whole country, but then we realized that the most the part where people were having the most hardest time when it was hot was like the dry arid zone. So we decided to focus on the most arid zone. And then we realized, just like the presentation earlier about the cooling system, is that the findings that we could make would probably help a lot of people, because this type of climate has the same problem pretty much everywhere, and it's completely spread around the world. And our main focus is social housing, because it represents most of the population of the country, and they are also the most affected and vulnerable social group. Well, these two photographs are two different settlements in one of the study within the study area. And the thing about these settlements is that even though one it's an irregular settlement and another one it's a regular, completely by the book settlement, they actually having the same type of problems. It doesn't, even though the one follows the normative, the other one doesn't. Following the normative doesn't seem to fix anything regarding thermal comfort and the effect climate change is having. And well, as you can imagine, this is just going to increasing the use of AC systems, especially during the warm season. So in order to fix this, or to contribute to the problem, to the solution, the research objectives is the objective of this work is to represent the finding, to present the findings in the relationship between climate variables and environmental performance of a free-running prototype dwelling located in the region of northern Mexico. And the study is the first stage of a research that aims to develop a method for the distribution of passive strategy for both cooling and heating based on building performance, and aim to provide thermal comfort whilst reducing energy consumption. So basically what we're doing is testing one model all across the country and see with what other things can we relate its performance, what can we use in order to predict that, so we can use these findings to them to later do some sort of climate zoning. Okay, so the methodology that we used for that was, first we took the study area and we divided using a theoretical grid of 50 by 50 kilometers, and 427 study points were established. And this was done to procure a homogeneous and evenly distributed data set for weather data. The following step was to obtain the weather data of each point in the shape of EPW file. This was done using Meteonorm and the interpolation function. After this, the weather files were processed, and the weather data from each file was associated with each of the point, like we can see in this slide. This is a yearly average temperature of each point. Then this is the average monthly maximum, in which we can see that, well, this thing that looks like an armpit, it's like the hottest part. And then the relative humidity, where it can, the aridity of the territory can be appreciated. And this thing also goes as the most dangerous or uncomfortable one. Then the next point was to define a digital building model, considering that most of the social housing in Mexico, it's built the same due to the normative. We pretty much established one model and tested all across the territory to see how it goes. The dimension and the occupation and the thermal properties of the model were elaborated following the data from the latest census statistics. And the original idea, or the original distribution, was taken from Elemental Studios incremental housing prototype, because it was developed for Latin America and it already was replicated in Mexico. And it has a lot of research behind it. So it was probably the best thing to do. The model has 54 square meters. It's a 3-bedroom house, and it has an average window. We choose an average window to wall ratio of 0.5. And in all of the cases was tested as a freestanding model, as a freestanding house in the middle of we could say the desert, in order to test the worst case scenario for overheating. Then the average U value was 2.86 watts per square meter Kelvin. And And it assumes the typical local construction methods, which is a concrete floor, brick walls with concrete and gypsum renderings, and a concrete slab as a roof, and single glazing. So, and then after having all this, what goes next is how to assess the comfort in that. And the thing is, Mexico, unlike other, or pretty much Mexico, like other developing countries, doesn't have a comfort standard. It has not been defined for it. So we kind of use a Franken method that we have been developing. This one is about to be published in a book that is going to be released next year, and Professor Susan Roff is the main editor of it. So the comfort assessment was done using the 5-step overheating assessed method for naturally ventilated buildings on top of the European, or what used to be the European standard EN 155-251. The idea to use these two was because the upper comfort limit of the European standard was took, and then a bunch of layers or criteria were stuck on top of that to assess so we could somehow assess or project the possible effect of passive strategies, considering everything is free running or can be as it is nowadays. So briefly speaking, the first criterion is to account for all the hours strictly above the upper comfort limit. This is the base of the pyramid. Then to account the hours above 1K, where very sensitive people and subjects can start to sense overheating. And the following criteria, step 3 and 4, are the hours above 1K and 2K, which are the hours where adaptive opportunities are still an efficient way to regain comfort. And the last step, the step 5, are the hours above 4K, where overheating is a severe problem or can be severe for sensitive subjects, and most people would be uncomfortable, and something needs to be done to regain comfort, because these conditions are not supposed to be endured for lost time. And this practically represents 39 degrees, so it can be very comfortable for a lot of people. This is how it looks. On the left, it's the graph of the operative temperatures obtained by the simulation. On the right is the one how the European standard considers, which is basically comfort, discomfort, and discomfort can be uncooling, overheating or overcooling. And then, but what we do with this is more like this, which is to assess the overheating hours according to their intensity, how far from the upper comfort limit they are going. And the other graph is just a way to represent the data. So at the end, this is what we were looking on each of the locations. The dotted line is a European standard, how it represents overheating, and the dark spots are the actual hours that we're looking at that we have identified as problematic. And these are after all that, all the simulations were executed using, and then the comfort assessment, and these were the results. On this slide is the percentage of timing comfort of each of the points, but we realized that this could be misleading because overcooling hours are also considered. So we rather look about all the percentage of time overheated. And we realized that a lot of the locations that we thought were arid are not necessarily that difficult. And the desert of Sonora and Baja is probably the most uncomfortable part of Mexico if you live in a free-running building. And then we start applying the method for assessing thermal comfort. This is the step 1 that is basically the same that the European standard. But then when we start applying the following steps, the data kind of became more clear, or the results, in the sense that, for instance, we can see that actually that if we were about to replicate this same building prototype everywhere, these would be the places where we would need to change this. But it's important to keep in mind that these results are only indicative for the purpose of the study, since the model only represents a small part or a small chunk of the housing construction. Because for the model we use fixed values, and reality is that social housing actually could have more like a range. So it's more like this was just a way to an experiment to see the correlation between the geographic data, which was the last part. So we took a bunch of features and the things that we thought it could have, and we correlate them with the results. And the results are that the altitude, it's one of the most, the values with the highest correlation. And it makes sense because there's a lot of altitude variation in the territory. But the ones that were most representative were like the yearly average temperature and the average monthly maximum. Well, first is the yearly average. This means that if we were about to make some sort of index, or if we were about to make some climate zoning, these three possible values could help. And probably one of the things that was motivating this, that I should have mentioned that before, is that the Mexican normative established a series of prescriptive norms by latitude. So this experiment was also to kind of assess if it was a good thing to do or if it wasn't. So these are the results. And the conclusions are that the geophysical factors, the factor with the highest correlation is altitude. The climate feature with the highest correlation is the average temperature. Then absolute minimum and average monthly maximum also for the highest correlation, but not as high as the others. Absolute minimum temperature can be used to predict underheating. That was something that we were not looking at, but then at the end of the day, it was a finding also. There is no correlation between Köppen's climate classification and the overheating distribution. So someone, I mean, that was more for myself, that the Köppen's climate classification cannot be used for this. And even though when climate data can be useful, building performance data is necessary to predict overheating. That's another conclusion, that you cannot predict how buildings are gonna behave just by looking at climate data. Building performance data needs to be put into the equation. And and the last one is that this method can be useful to detect and identify specific areas where more sophisticated passive strategies are necessary, in the sense that this was just a building envelope and a control space, we could say. But in these areas with overheating is detected, other features such as a more robust building envelope or evaporative cooling can be used to try to see if comfort can be better without so many time in overheating. And that's it. Thank you.
Thank you, Daniel, for your presentation. I think this is a good project to develop your PhD dissertation. And now the last presentation is a video presentation. The speakers are Dr. Naima Benkari, Islam Salam, and Waud Al-Araimi for Sultan Qaboos University. And the presentation is entitled Characterization of Bioclimatic Properties of Vernacular Statements in Oman for Future Applications in New Design with Hot, Harshest Climate. We'll try to run the presentation.
Good morning, everyone, and welcome. My name is Waud Al-Araimi, and our presentation today is about the characterization of the bioclimatic properties of vernacular settlements in Oman for future application and new design in hot, harsh climate. The necessity to derive sustainable building solutions from the local vernacular architecture is being increasingly asserted about the immense energy consumption, natural resources depletion, and high levels of greenhouse emissions. Our research will assess the bioclimatic properties of the Omani vernacular settlements and their efficacy in terms of turbulent content. So the content of this presentation will start by the introduction. we move to the methodology. We will showcase some case studies. And also we'll talk about the implemented passive strategies and the selected case studies. Moreover, we will also see the commonalities of passive design used in the 3 case studies. Then we will conclude our presentation. Since the 1970s, Oman is witnessing a rapid urban growth as a result of the oil discovery and commercialization. Consequently, the country's economy transformed from agricultural trading to exclusively relying on oil revenues and imported technologies. These factors contributed to the gradual version of the pre-oil era settlements and the abandonment of the traditional modes of habitat. With its 4 different climatic zones, Oman vernacular architecture has provided forages thermally comfortable spaces, adequate ventilation, and natural lighting, with a limited need for energy consumption. In this presentation, we shall highlight on Zone 2, which is the hot, dry climate, which is the most dominant climate typology in the country. Research about sustainability in the built environment is increasingly focusing on finding solutions to reduce energy consumption and greenhouse emissions. The studies on the bioclimatic properties of the vernacular architecture are an important component of this research field. Since the 1960s, different parts of the world were investigated by these studies through qualitative approaches, quantitative methods, and the combination of both. The article of Al-Hana'i in 93 evoked earlier is the first published research that examines the bioclimatic property of vernacular architecture in different regions of Oman, considering the country as 4 main geoclimatic regions: the coastal, mountainous, desert, and southern regions. This study presented a qualitative review of the climatic responsive properties of the traditional houses in each zone. The study made the case of important role played by building designs, research about sustainability in the built environment is increasingly focusing on finding solutions to reduce energy consumption and greenhouse emissions. The studies on the bioclimatic properties of the vernacular architecture are an important component of this research field. Since the 1960s, different parts of the world were investigated by these studies through qualitative approaches, quantitative methods, and the combination of both. The article of Al-Hana'i in 93 evoked earlier is the first published research that examines the bioclimatic property of vernacular architecture in different regions of Oman, considering the country as 4 main geoclimatic regions: the coastal, mountainous, desert, and southern regions. This study presented a qualitative review of the climatic responsive properties of the traditional houses in each zone. The study made the case of important role played by building designs, forms, volumes, and orientations, architectural features, courtyards, transition spaces or windows, and construction materials, mud, brick, stone, fronts, to formulate recommendations for climatic responsive and energy efficient new constructions. On the other hand, Majid in 2012 studied the design parameters of samples of old and new houses in Oman based on the data collected about indoor temperatures and inhabitants' behaviors towards heat sensations. The paper makes the case for the necessity to explore the properties of the vernacular architecture as a precondition to develop a built environment in Oman that is adapted to its climate. Now we move to the methodology. Follow a comparative methodology in which we've selected 3 case studies. The first case study is Hara Qasra, the second case study is Hujrat Musalman, and the third case study is Hara Seja. We then observe the different passive design strategies which are common among those 3 case studies, and finally, the possibility of implementing the passive design strategies in modern building design. So our first case showcases Hara Qasra in Al-Batina region, birthplace of Nasser bin Murshid. The Hara comprises of some great houses, wells, villages, and streets. It also has a great touristic and cultural potential. So the settlement of Qasra has a northeast orientation, and it occupies an area composed of date gardens and residential quarters. The Hara consists of around 15 buildings and 2 entrances. Each of these buildings has a name that it was known with. These names either reflect the building size, function, shape, or location. Hara Qasra also consists of mosques, but they were situated outside the Hara. So the main spine that changes according to the topography is usually shaded throughout the day, which makes it thermally comfortable and pleasant to users. Temperature differences between the spine and the outer area generates cool breeze in the pathway, which is from the east direction in the early morning time and then changes direction in the late afternoon, and it's from the west. The construction of the Hara is built using sarouj blocks and palm stalks, having a village that is integrated within the green oasis surrounding the Hara with different types of trees and vegetation. This creates a microclimate around the settlement and increases the feeling of thermal comfort among users. Here are some of the elevations of the Hara from the east and west direction. Our second case study is Hujrat Musalman. Musalman is part of the light Wadi al-Ma'awil in Al-Batina region. It is not far from the famous port of Nakhal. So Hujrat Musalman presents a considerable importance for its historic context, as well as its unique typology. Hujrat Musalman was inhabited for more than 400 years of continued settlement. Hujrat Musalman has a peculiar spatial organization and a specific urban and architectural components. It was built on the southern edge of its oasis. Hujrat Musalman also used to be surrounded by a solid defensive wall preceded by a moat. The Hujra is composed of around 25 dwellings. It has 4 towers. It also has 2 mosques, Jama' Hudayma and Jama' al-Jama' with its madrasa. Hujrat Musalman also had a souk formed of 20 shops belonging to the Hujra residents. Moreover, the thermal properties of the house of one of the houses of Hujrat Musalman, Beit al-Khandaq, is studied in another presentation in this conference. So the primary character of Hujrat Musalman of becoming a defensive architectural typology, which takes into consideration the passive strategies for thermal comfort. The irrigation and water supply relies essentially on village Musalman of 4 to 5 kilometers long. The town walls and towers were built in the same period as Hujra itself, roughly 4 centuries ago, with the same materials of construction, stones for the foundation and footings, mud bricks, palm trees, and cedar wood. The main construction material is common for all the buildings of the Hujra, which is mud. The brick is composed of mud and straw or grain husks, especially wheat. The roofs are built on a wooden structure made of trunks of palm trees or cedar trees. A wooden net of palm leaves put on the structure would contain the layers of mud and pebbles that would form the core of the roof. Looking at the architectural typology and general organization, the remaining residential buildings in Hydrofluorocarbons varied from the double-floored cheerful mansions to more simple dwellings with double or triple spaces. Both types of dwellings follow the same general organization where the spaces are organized, aligned or around a courtyard, locally called al-bahu. In cheerful dwellings, one can see the split openings, marami, ventilation windows, muruk, pointed arches, frozen with integrated windows at the base. The windows of these houses are located at the bottom and niches at the top to serve ventilation purposes. And here are some of the passive design strategies that have, which are the irrigation water supply, azote materials and techniques of construction, the dwelling designs with the climate, natural ventilation using the dwellings and proximity. So our final case study is Hara. Seja is considered to be the most important settlement in Samail in terms of its size and importance. Its history can be traced back to the pre-Islamic era. So this is the layout of Hara in Samail, and as you can see, it takes an orientation of a northeast orientation, and it is located at the edge of the western Hajj. So there are specific characteristics of Hara. Its uniqueness. First, the contour. The difference between the lowest and the highest point in the Hara is around 26 meters. Having a sophisticated water network, Seja benefited from a well-designed water system. The urban fabric, appropriately connected with ventilated walkways adapted to the terrain. Dwellings of the Hara are detached and some are attached within the urban fabric. Most of the houses were built with mud on base of stone. The dwellings are relatively small in size. The fourth characteristic is the size. The Hara lays horizontally at the edge of the mountain, and it's around 190 meters by 17 meters. The location of the Hara is surrounded by two main features, mountain range and farm field, and is mostly isolated and away from the main road, making it a suitable sanctuary. Moreover, most of the entrance of the spaces was through the network of walkways, and since most of them were attached and within the urban fabric. Their window openings were overlooking the walkways. The entire Hara seemed very well connected because of these walkways, and the cluster were clearly defined. These walkways also helped in inducing cross ventilation as they are in the direction of the prevailing winds, northeast. They also had smooth curves which allowed the wind to flow freely throughout them. Gathering spaces are known as sablas, and they are very important spaces in the Romani culture. These are seen in Hara Seja, and the unique character of these spaces is that they are properly ventilated, and also they allow for adequate daylight to enter into the space. Here I present one of the houses in Hara Seja, which is Beit Al-Ain. It has a defensive character with very few windows to reduce the thermal heat gain. On the other hand, it has many ventilation openings surrounding all the facades, and this affects the level of the interior light inside the space. Looking at Hara Seja water system, Seja received effectively high amount of precipitation because of it having a well-designed water system. Water system that would not only properly direct the rain as it arrives from the mountain, but also store it so it is later used by the inhabitants of the Hara. Here we can see the elements of the water system, which comprises of a lane, also al-farda, which is an opening similar to a well, and it is from where the village is accessed by the responsible or workers for checkups, cleaning, or maintenance. Al-majaza, which is an opening where the inhabitants access the village for domestic usage of water. It is generally surrounded of walls and without a roof. And as you all know, the village, which is a channel of running water, and it is used for domestic and agricultural purposes. The village in the Hara goes through the farms, and trajectory is punctuated by small mosques so that its water is used for ablution. On this slide, I present the commonalities in passive design strategies among the three Haras. So what we can see is they have common the compactness of the urban form. They are all compact in size. The building orientation, they take the northeast orientation. They all have natural ventilation which acts for cross ventilation, stack ventilation, single side ventilation. They allow for natural light control. They have a high thermal mass, evaporative cooling, presence of village, other sources of water near or inside the houses. The use of light color for light and the heat reflection, the thermal insulation by material, thermal insulation by design, which is through shading devices, transition spaces, courtyards, balconies, galleries, and doorways. The thermal control by design, height of interior spaces, size, frequency, orientation, and location of openings. And the next slide, I will talk about the construction material within some of the houses in the Hara. Here are some examples of the construction techniques used. For example, you can see the walls are constructed of saruj from the outside and the inside, and also having a 500 mm mud brick. So it gives the thickness of a wall of 600 mm. Then you can see here also the thick walls and roof construction. Also to reduce the high solar radiation, especially wasp and horizontal surfaces having a compacted urban fabric. This helped to reduce shade, to create shaded passages and facades, and protected the walls from direct radiation. The use of limited number of openings with wooden louvers, limited glazing. The use of natural cross ventilation through courtyards and high openings helped in balancing the high average temperature and humidity. So in conclusion, findings highlight the role of passive design strategies such as massive structures, proper orientation of the openings, shaded transition spaces, and courtyards in making the indoor spaces sensibly more comfortable than what is offered by the construction market today. Certain important features for passive design strategies need to be further investigated in order to evaluate their effectiveness in new building designs to passively achieve the required thermal comfort. More research is also required for the properties of local construction materials in new sustainable construction systems that can have equivalent thermal mass as the vernacular constructions with less walls or roof thickness and weight. Moreover, there is also a need for similar investigation of different typologies and designs. Thank you very much. I hope that you've enjoyed the presentation.
Many thanks for all the presenters. Share this session was easy. The presentations have been very well structured and the time available have been well used and adjusted. Now, Professor Fetwi will lead the question and answer session. Thank you.
Yeah, thank you very much, Jessica, for leading the presentation sessions. Yeah, the time management was great, and thank you all presenters for the concise presentation and wonderfully presenting your contents. So now we go directly towards the question and answer. I just have just slide I will project so that you will answer the questions which are asked by the audience. Yeah, I hope you can see my slide. So yeah, can you just give me a note if you can see my slide?
Yes, we can see.
Sure. Okay. So the first presenter, Ahmed. So we have few questions to you, which are forwarded from the audience. So maybe you can proceed by reading the question, then answering to it. Yeah.
Yeah, sure. So the first question says, do you think this prototype is suitable for our climates? What happened with hot and humid climates? So basically the device is designed for hot, dry climates, not for hot, humid climates, but we are now working on developing the prototype to work for humid climates. And then the second question, did you compare the performance with the other zero refrigerant cooling devices? Yes, so the other zero refrigerant cooling devices are not meant for cooling bigger spaces. It's focusing on smaller spaces as I presented in the presentation. Therefore, the main comparisons were done with conventional air conditioners. But to go to the point of your question, there is no any existing zero refrigerant cooling device that is capable of cooling like residential spaces, there's not even a pattern for any of them after we checked it with it. And then the last question you mentioned about an increase in humidity in your result. Why do you think this is so? So actually, it was one of the purposes to increase the humidity because the device is meant for cooling hot, dry climates. So we are adding water to the device through the evaporative cooling pad that's like biomimetic designed. And that was one of the purposes. So yeah, this result is meant to be achieved. I hope I answered all the questions briefly.
Yeah, thank you very much. I think you did well. Yeah, so since there is no any other questions so far, then we proceed to our second presenter. All right, so I go to the second presentation. Then I think to second presenter, paper number 73. Again, you may proceed by reading the question, then you can give us your response toward this question as well.
Yes, thank you. The question, the answer is productivity is ask the questioners. So it is maybe less accurate than the doing tests, and B1 is Office B1 is may be many workers use PC, so PC display is growing. So I think they can work the place. So then other workers don't use PC. So it is answers my questions.
Okay, thank you very much. So hopefully the question is responded well. And then again, I go to the third presentation where we have one question towards that as well. Maybe Daniel, can you respond to this question?
Yeah, well, the short answer is that now it's just theoretical. It doesn't have actually a practical outcome. The most practical it can be if someone needs to, it's trying to see how to apply the passive strategies on a space, how to make the spatial distribution of these strategies. This could be useful for them. However, the results by itself, they don't pretty much do anything. I think that's it.
Yeah, thank you, Daniel. I hope it is well answered. Then we proceed to our fourth presentation. Dr. Neema, you have a good time now to engage your audience. And we have 3 questions here. So hopefully, your colleague was trying to respond to some of the questions, but it's good also to engage in this way. So please have your, back to you, Dr. Neema.
Yes, thank you very much. Assalamu alaikum all. I'm sorry because I'm on a site visit. So we thought that it was more appropriate to record in case we don't have enough or a good network. I just saw the last question of Sue coming up. I did not have the time to read it. If possible, Doctor, you add it. I'll try to answer the 3 firsts. Dr. Islam had given some short answers about them. So sarouj is a material. It's like a clay material that is, like you said, Sue, it is extracted first from either the mountain or from the wadis, and then it is burnt following a traditional cycle. And to make it more, to increase its reactivity, to become like a cementitious material. And it is applied in Oman, especially in the northern part of Oman, as cladding material mainly. But in some rich houses, even the bricks, the bricks that make the walls are made out of sarouj blocks. So we can have it as a powder, and then we can reform the resulted powder into blocks. And here you have very solid and firm walls. And the role of sarouj is not only for structural purposes, but it's also for insulation, humidity insulation. It absorbs and retains the humidity. And also it is an insulation purposes as well. Today I'm in Qasra, in one of the houses of the first settlement we presented. The house is not, doesn't have any electrical AC air conditioning. It is all natural ventilation. It is Dhuhr time, so it is the peak in terms of temperatures, and I'm sitting in the room very comfortably, not feeling hot. I'm just comfortable. So this is due to the sarouj, and also of course to the thickness of the wall and the orientation of the cross ventilation that we have inside, and also the ventilation that is generated from the settlements. And this is what we wanted to highlight by taking different settlements and how they are, the layout is adapted to, of course, to the topography, but also respects the orientation of the air, of the cool air. There was also a question about the timber. Yes, it is a structural, when we did the pictures, now it started, this house is being restored now, but the pictures that you saw are all from the old house before restoration. So the structure is like Prof. Somian has explained it in the session, in his session. It is quarter logs of palm trees that are the main bearing elements, and then you have a layer of native mat, and then the compact soil, etc. The last question, I did not have the time to see it. It was added when I will just go back.
I have it here.
Okay.
Yeah. It says that in the last case study settlement above the oasis, does the village benefit from anabatic winds drawing cooler, more humid air up through the settlement powered by the heated south-facing mountain slope above it? This is the question.
Yeah, just to address the before last one, the Sarouj more waterproof than usual. Oh, yes, of course, it is much more waterproof. And I am in a house that has 300 years, and some parts are original Sarouj. There is, it is of course, we see the traces of aging, but it is we don't see any decay, any signs of decay. The last settlement, which is Seja, yes, the work with the heat and the cool throughout the day decided the orientation and the orientation of the streets that are irrigating the settlement in order to have to suck the water, to suck the fresh air from the oasis during the day, during the afternoon, and avoid the hot air from the mountains to get inside, because it gets heated throughout the day. So there is this turning air current that is taken advantage of.
Yeah, okay. I think it was great having you, Doctor, for explaining everything which are raised in the chat session. So
I would have loved to have you all visit this this house here. It would have been really interesting for all of you.
Yeah. Yeah, let me get back to the session then. So I think we are running out of time as well. So if there is any more questions, then thank you very much, everyone. And
thank you.
Yeah, it was great. And I would like to thank the co-chair as well, co-host, co-chair, and for the conference organizers who give us this forum to share our thoughts and our ideas. So thank you all. It was a pleasure meeting you, everyone. Thank you.
It was a pleasure to spend my time with you. And I hope we can see you each other at the next conference in 2023 in Russia.
Yeah.
Yes.
Thank you very much. Bye.
Thank you.
Thank you.
Thank you very
much. Okay. Bye-bye.
Bye-bye.
Okay, bye.